Hello, so welcome to linear algebra. That's the first of a series of lectures on linear algebra, very quick. So we'll learn about real matrices, complex matrices, a lot of things, and some tricks at the end too. So let's find this presentation first. Yeah, so real matrices and their properties. It's going to be about real matrices today. So hope it won't be very difficult. Normally, I'm teaching calculus a lot for 25 years. I perfectly know what are the difficulties. So I taught and learned calculus in many places, many countries like Romania, France, United States too. So I perfectly know what's difficult and what's not, and we'll have things made in a simple way. So let's start with the difficult problem. So what's the formula of the rotation of angle T, right? So by rotation, I'll take it as mathematicians do counterclockwise, you see. So that's a formula with cos t and sinus t, and it's very easy to mess up things. So best is to find the formula every time you need it, in case you're not able to memorize it. Actually, I'm like this. I'm never able to memorize it. I find it in 2 seconds every time. So the trick is that the points in a complex plane can be represented by vectors, right? So in the formula, which to any vector xi associates the vector xi rotated by t, right? And now the thing is that's a trick of linear algebra, is that many transformations like symmetries or projections can be written in this form. I mean, you take xy, you're just throwing some coefficients here. You take a linear combination of x and y, let's call it ax plus dy. And on the bottom, I throw in another combination, cx plus dy. So you see, every time I have four numbers a, b, c, d, I have a transformation of the plane. Even my xy goes to this guy here. And well, these four numbers, actually, you can put them in a so-called matrix, a 2 by 2 matrix, and that's the formula. I mean, every time you have numbers, a, b, c, d, and a vector, you can construct this vector. So, well, let's see if the rotation, so that's a trick. I mean, let's look for a formula for the rotation of this type. It might exist, it might not, we don't know. So let's look for it. So that's the matrix we want to construct. Another thing is that let's look at the basis on 1, 0, which is the vector here. This must be rotated by t, right? So the coordinates will become simply this and this. These are cos t sinus t. So our transformation must satisfy this. Now let's look at the other vector, the one on the vertical, 0, 1, okay? So this goes rotated like this. So we'll have the x coordinate will be negative, minus sinus t, and the other coordinate will be positive, it's going to be cos t. So we're looking for a matrix, our ABCD is here, satisfying this and this, and there's no choice. I mean, this formula here gives you actually the first row of the matrix, so you just have to plug in this here and this here. I mean, if you think of it, that's the only way it can work. So our rotation, if there is a matrix for it, that should be the matrix. There's no other choice. Now the problem is this matrix the good one or not? I mean, it can only be this. But what we know is that the transformation associated to this matrix maps 1, 0 into its rotation by angle t. That's what we did first. And also 0, 1 it maps in what it should map, I mean, the rotation. But probably now, if you take some other vector, let's say 50, 132, will it get rotated by this matrix RT in a good way? And linear algebra tells you that it's okay. So that's a theorem that I'm using here. We're done by linear algebra. Okay, so this was an application. You see, you can do it. It took us how many, 3 or 4 minutes. For me, it takes 10 seconds every time because I'm used to this. I can get right away this matrix here because I know a bit linear algebra. So I'll try to explain you all the things that I'm using here. So you're using matrices, and this kind of thing. It's a kind of product between matrices and vectors. And also we're using the theorem here that whenever your matrix is good, your transformation on 2 points, 1, 0, and 0, 1, let's say, it's good everywhere. So we're using a bit of theory here. So this was an introduction. Now let's go a bit slowly. So we're interested in linear maps. By linear, I mean which map the lines going through the origin through lines going through the origin. Like the rotation is, of course, like this, maps lines through lines, also symmetries, projections, many other things. So the theorem of linear algebra is that these linear maps are exactly of this form, the ABCD being some numbers. I mean, it's a so-called linear combination of x and y here on top, and the combination of x and y on bottom. Now, well, these parameters ABCD, you can put them in a matrix, so it's better to make this convention. It's a convention, so every time I have a 2 by 2 matrix and a vector, I can multiply them and I get this guy here. So with this convention, the theorem simply tells us that the linear maps are those of the form f of v is a v, right? That's what's written here. F of a vector v is a guy like this, which is the vector multiplied by a matrix. Okay, so with this multiplication convention, that's our theorem. The linear maps are f of v is a v, that's all. Now, let's see some examples of this. So the identity map, what is the identity matrix? I mean, if you put 1, 0, 0, 1, with this multiplication convention, it's just the identity. Also, let's take now the all zero matrix. Let's see what we get. Well, of course, we get 0, 0, so we get the null map, okay? So the identity map corresponds to this matrix called the identity matrix. The null map corresponds to this null matrix. Now let's take something more complicated, like the projection of the horizontal axis, okay? How does this work? I take an xy, and it just kills the y, right? So xy goes to x0. Now let's find the matrix. So what should I put here in order to xy go to x0? Well, it's a bit like before, you have to guess the coefficients here. There's a system there, you can solve it in your head and get 1, 0, 0, 0. Okay, so the projection on the horizontal axis is this matrix here. Similarly, on the vertical axis, it's 0, 0, 0, 1. Once again, you can do it in your head. It's a system to be solved. It's very easy. Now, one more example. Let's take the diagonal, x is y, and the symmetry with respect to it. So the symmetry just flips x and y. So that's the formula. xy goes to yx. So once again, what's the matrix to be put here? Well, if you think a bit, 0, 1, 1, 0. I mean, it works, right? This times this is y, and this times this is x, so it works. And of course, we have also the rotation of angle t. Let's go back to the formula. Yeah, that was the formula. So you see, 2 by 2 matrices are really very simple. I mean, usually you can do things in your head, and all these computations like identity, projection, symmetries, even rotations, you can more or less do it in your head as you become more and more advanced. It's very quick. Now, let's go to n dimensions. Now, we're mostly interested in 3 dimensions, right? That's where we live, in 3 dimensions. So 2 dimensions is more or less for, as an introduction. I mean, it's for joke. I mean, we're interested in 3 dimensions, okay? Now, 3 is quite complicated. So it's actually better to do it in n dimensions, because n dimensions is not that much complicated than 3. And sometimes even things become simpler somehow because it's a bit more abstract. Plus, it's useful if you do more advanced things like physics, whatever. We'll do that later. So yeah, let's do it in n dimensions. So, well, the theorem is exactly as before. The linear map from Rn to Rn are those of this form. So you just take your vector and linear combinations for these guys, right? Now, the coefficients, so you need how many coefficients? N here, n here, and here, so n square coefficients. It's better to put them in a matrix. And as before, let's just say that this matrix multiplied by the vector is this beast here by definition. So with this convention, this theorem just says that the linear maps are f of v goes to v. That's all. So once again, examples, well, in dimensions, we have symmetries, rotations, all that. Let's just take a very simple example. It's the all-one matrix, okay? So never be afraid of that all-one matrix. It's very simple. Let's try to work this out. So how does this work? Apply to a vector, it's going to sum everything, right? You see, let's go back to the formula here. So if I put only ones here, all the a's are ones, I get sums everywhere. Okay, so what's this map now? You take a vector and you sum everything. It looks a bit bizarre, and there's a trick here. Let's just divide everything by n. Okay, so 1 over n, what was said before, is this vector over n, which means it's a multiple of the whole one vector, and the scalar is just the average of the numbers. So now my claim is that this is just a projection on this vector here, or one vector, because the whole one vector, I mean, it goes to itself, and anything else you just average, and yeah, it's just a projection, okay, from 1, 1, 1. So as the conclusion of all this whole one matrix here, which might look a bit scary, I mean, it's not the identity, it's something different, and people usually tend to forget. It's just n times the projection on the whole one vector. So something very simple. Okay, now, well, some theory now. So the problem, the difficulty somehow in all this is this multiplication formula. You see, yeah, the things here, I mean, they look very bad. So let's understand how matrices multiplied with vectors multiply with vectors. So best actually is to multiply matrices by matrices uh, in the following way. So I take rectangular matrices, Mn and then K. So then here should be the same as n here. And the thing is that you can make a product and you get an M times K matrix given by this formula here, which looks quite horrible. The idea, what I'm doing here, I'm multiplying the rows of the first one and the columns of the second one. Okay, that's what I do. So that's a very general definition. Now, well, you can do it better. Let's try to simplify it. So my claim is that using the matrix notation, so Aij means entry on the ith row and j column of the matrix. The formula is just like this: AB entry ij, sum over k, aik, bkj. Why? Because let's go back here. So see, let's take here. Here I is 1, j is 1. It's a sum. It's just a simple sum. And what varies is the index in the middle here. You see 1, 1 goes up to n. First is fixed. So exactly what everything here is a sum of n terms that varies in the index in the middle. So you see, with this notation, I mean, this formula here, all this slide here, we don't need it anymore now. It's right here, okay? So that's the final formula of matrix multiplication. It's a bit abstract, but you see, it is much, much simpler than what we're doing before with these big matrices. So that's the formula I need to know. Now this, well, this is a rectangular now. So in general, the linear map from Rn to Rm and M difference are of this form: multiplication by rectangular matrix. Well, as before, I mean, that's a series of statements that are become more and more general. So in order to not mess up the sizes, always perform a size check when you write something like this. So let's do a size check. So my input is a vector from Rm. So that's a vector like this. It has how many? M rows and 1 column. So it's a M times 1 vector. I apply to it an n by a matrix. So this guy here should be this guy here. It's my M. And the output is a n times 1 matrix. That's exactly a vector of Rn. You see? So that's how you get the dimension here. I mean, sometimes you say it's n times m or m times n, but it's n times m because if you do the size check, this guy here should be equal to this guy here. Okay. So that's the result. Now, what else can we say as theory? Importantly, the product of matrices corresponds to the composition of linear maps. If I denote by f sub a the linear map associated to matrix A, then I have this formula here. Whenever I compose two linear maps, the matrices get composed. proof, well, just do some computations there with this formula here. It's very simple. Now, as an application of this, let's try to invert a linear map. So let's think a bit. I mean, I have my FA, let's say, my linear map, and I'm looking for B such that this is the identity. So this means AB must be the identity matrix, okay? So as a consequence of the first term, I have the second one. The linear map is invertible when the matrix which produces this map is invertible. And in this case, in order to invert, I just have to invert the matrix, right? Because I plug in here B is A minus 1, and it works. So let's see an application of this. 2 by 2 matrices, that's the formula. That's how to invert the 2 by 2 matrices. So how to invert any linear map in the plane, because these come from 2 by 2 matrices. So how to prove this? If you ever forget the formula, well, the proof in your head, very simple. So when AD minus BC is 0, it won't work because the columns are proportional, so it's not going to work. Now, if it's not 0, the trick is to look for a formula of the inverse of this type. So, which means I have to take my matrix with the stars here, multiply by ABCD, and I should get AD minus BC times the identity. Also, some equation is pretty clear. You see, in order to get AD minus BC here, definitely I must put D here and minus C here, right? So I get my first column, the same from the second. You can do it in your head every time in the formula. So that's the inversion formula for 2 by 2 matrices. 3, 3, 4, 4 is more complicated. We'll get into that in further lectures. Now let's talk about one more thing now, which is important. So that's just the first lecture. It's an introduction to everything. So assuming that AV is lambda V, I mean the matrix A multiplies in the direction of V by some lambda. We said that V is an eigenvector, lambda is an eigenvalue. So this is very important. I mean, because the matrix is very, very simple in that direction. It just multiplies. So let's see some examples of this. The identity, well, of course, I mean, it's lambda is 1 everywhere, right? Multiplies by 1 everywhere if you want. Same for the null matrix, I mean, multiplies by 0 if you want, because that's the output vector. Now for the projection on the horizontal axis, you can do it either geometrically like this or solving the equation here. So either lambda is 0, then your vector must be like this, or lambda different from 0. Lambda different from 0 means that y is 0. And then lambda must be 1. So that's, you see we have different things here. So this matrix is 2, the null and the identity have only eigenvectors. This one has 2 different eigenvectors. Now for the symmetry with respect to the axis, y-axis, once again, I can solve it as one eigenvector with eigenvalue 1, and another one with eigenvalue minus 1. That's quite tricky. Now here's a transformation which has nothing at all. I mean, well, it has only eigenvectors for lambda is 0. This tricky matrix here, 0, 1, 0, 0. And now finally for the rotation, of course, we won't have eigenvectors except for 0, 0 itself, because it can be proportional. So this is important. So the good case now is when the matrix has n distinct eigenvectors. I mean, which form a basis, a new basis. In this case, of course, in the basis, the matrix is just diagonal because in each direction multiplied by lambda I. So these are some of the simplest matrices. And the problem is, yeah, which matrices are diagonalizable and how to diagonalize them. So getting back here it's okay, here it's okay, here too. Here it's okay for a symmetry. Here is not okay. This is not diagonalizable. The rotation is not either over the real numbers. So we'll talk about all this in the next lectures. See you soon.